Hey everyone! This video is going to be over assumptions, which is the fourth and final step in data screening. I have already recorded the other three steps in data screening, which are accuracy, missing data, and outliers. So if you are having problems with any of those steps, you can go to any of those videos for extra assistance. I have also provided a PowerPoint so you can follow along and make any personal notes if you wish. So in this video, I will describe what assumptions there are and how to screen for them. Now, the study is still the same as the other videos, and I will just briefly go over what the study is about so people who haven't watched the other videos can still listen to this and not be lost. So for this video, I am using some fake data. So in this fake study, we were looking to see if stress and anxiety predicted memory. So participants took an anxiety test to assess their respective anxiety disposition. Then participants were given 5 minutes to read 3 scenarios. Next, participants took a memory test. And then after the memory test, they rated how stressful the memory test was. So for this fake study, the independent variables are gender, which is categorical, anxiety, which is continuous, and stress, which is also continuous. And then the dependent variable is memory, which is continuous. Now, if you're confused with the IVs being continuous or anything about this data, don't panic. If you're running a t-test and ANOVA or whatever you are running, these basic rules and steps for data screening are still the same with a few exceptions. But really just focus on if you are understanding the steps in data screening. Don't focus too much about the study, because you may not have gone over having more than one IV, or if your IVs are continuous. So in general, data screening for the most part has the same basic steps and rules for all analyses, with a few exceptions, and we will get to some of those exceptions later in this video. So I'm going to go ahead and go to my assumption slides really fast. So once you have fixed your outliers, then you move on to assumptions. Assumptions are things we assume that affect the outcome of a test. So these are the rules we expect to have in place for the test to be accurate. Now for this part, I will cover all the assumptions just so you know what they are, but remember the assumptions you check for depend on your test. So you might not need to check all the assumptions for each test. It just depends on the test that you are running. Now the first thing I want to check before I check my output is multicollinearity. The assumption name is additivity, which means that each variable adds something to your analysis. Now in my outliers video, I went over why I didn't select plots right away because I didn't want to accidentally use the wrong plots. Well, I'm still not going to select plots just yet because this step may or may not change my plots. So if you are needing to check the multicollinearity assumption, then I would wait to get your plots until this step is done. Now, you wouldn't check for this assumption if you only had one DV, because there's nothing to compare to see if they are both adding something because there is only one DV. So don't check for multicollinearity if you only have one DV. However, there are exceptions to this rule. So an example of an exception would be this fake study. This fake study is a multiple linear regression. If you only have one DV, but for your analysis you're running an actual regression, then you still check for multicollinearity. If you're confused with what a regression is and such, don't really focus on that aspect because I'm sure you will get to that later on in the semester. So just focus on if you are understanding multicollinearity. So because my study is a multiple linear regression, I still check for multicollinearity even though I only have one DV. Now the reason for that is because I'm using two predictor variables. And when I say predictor variables, I am talking about my IVs. So if you remember in the beginning of this video, I said that for this fake study, we wanted to see if stress and anxiety predicted memory. So stress and anxiety are my predictor variables. Now, using two predictor variables that are the same, so stress and anxiety, will lower your power overall. So using two predictor variables that are the same will lower your power overall, and one of the variables will appear not to be predictive. So you want to make sure they're not too highly correlated to avoid this problem. Now, if you are not running a regression, but you still have more than one DV, you don't want your variables to be too highly correlated either, or you are wasting your time. Each column needs to add something to the analysis, and if the correlations are too high between two variables, then that means you only need one of those variables instead of both of them. So, to recap, you don't check for multiclinarity if your IVs are not continuous, so like categorical, and when you only have one DV. However, you do check for multiclinarity if you have more than one DV, regardless if your IVs are continuous or not. And you also check for multiclinarity if you have one DV plus your IVs are continuous because of the power issue that I just mentioned. And just to clarify, in my outliers video, I didn't go over outliers for regression because that involved extra steps and extra outliers to check for. Multiclinarity still involves the same steps no matter if you are doing a real regression or if you are doing an analysis with multiple DVs. So because outliers are already tricky, I didn't go over outliers for a regression because that would have involved extra steps. Plus, I wanted to make these data screening videos as basic as possible. So I'm going to go to Data View, and to check for multiclinarity, we go to Analyze, Correlate, and Bivariate. And we want to move all of our continuous variables over to the variables box. And we're going to go ahead and select OK. Now, in this table, you want to look for where it says Pearson's correlation. So where it says Pearson's correlation, you want to look over. And it doesn't matter if it's significant or not. So right here it's 0.526, so that's not significant. That doesn't matter. You also want to ignore the ones. That just means that it's correlated with itself, and so you expect it to be a 1. So you, where it says Pearson's correlation, you want to look if you have a number of 0.9 or higher. Now, another one of those exceptions I was talking about earlier was repeated measures. So this varies a little bit depending on what analysis you are running, like I had mentioned earlier in the video. So with our repeated measures, a really high correlation might be 0.99, and a really low correlation for repeated measures would be less than 0.10, which means you lose power. So this rule does change a little bit depending on what analysis you are doing, but generally you look for 0.9. So you would look across to make sure you don't have a correlation at or over 0.9. So let's check. So for this, it's a 1 because it's correlated with itself. That's fine. For stress and anxiety, the Pearson's correlation is 0.066. Now, yes, it's less than 0.10, but this isn't a repeated measures, so we're fine. In repeated and anxiety, or memory and anxiety, sorry, is 0.172. We're fine there. And then anxiety and stress, 0.066, which is the same as this. We had just checked it earlier. And then this is 1 because it's correlated with itself. And then memory and stress is 0.733, which is still fine. And then these down here we've already looked at. So memory and anxiety, 0.172. Stress and memory, 0.733. Those were fine. We'd already checked those. And then we have the 1 because it's correlated with itself. Now, if you have a lot of columns and you don't want to look through each one, then you can double click somewhere on the table and go to Edit and go to Find in Table and type in 0.9 and then hit Find Next. Now, it did nothing. It said that the search string 0.9 was not found. And that's because there were no 0.9s. But if there were, then it would just highlight that number for you. It would just highlight that number for you somewhere in this table, and you could see it. And you would just keep hitting Find Next until it told you that the search string 0.9 was not found. So what happens if you have two items that are too correlated? Then you would just want to pick one of them because they're technically not adding anything different to your analysis. So if you pick one, then now you just have that one variable that is adding something instead of having two variables that are adding the same thing to your analysis. Or you could average them together. Now, whatever you decide, so if you want to average them together or just use one of the columns, then you will have to rerun the fake regression analysis with either the average column or just the one column. And that is why this step is between outliers and assumptions, and that is why I still didn't select plots, because I may have had a column that needed to be deleted. And if you delete a column, that affects your assumptions. So that's why I suggest waiting. Now, I didn't need to delete any of my columns, so I'm going to go ahead and go into my plots. So I go to Data View, and now once you have figured out multiclinarity, you can check the plots, which is what I'm about to do. Now, because this is not a regression video, and this is just a basic data screening video, I am now going to pretend this is not a regression like I have in all the other videos. I didn't with multiclinarity because it didn't add any extra steps, so it didn't matter pretending if it was a regression or not because it didn't change any of the steps. So to get the plots, I'm going to go to Analyze, Regression, and Linear. And I don't need to change, like this is all the same from my outliers video when I was doing the fake regression. So I'm just going to go ahead and go to Plots. And in my Y box, I want to have zprid. And in my X box, I want to have zResid. So what is all going on when we're doing all this? Well, we are creating a scatter plot of the residual values against the predicted values. So zprid is the predicted value for the fake regression because we are now pretending this is not a real regression. So people can use this video to help them understand data screening. So we aren't going to focus on the regression part of the study. Anyway, zprid should be random because we are predicting from a random data set. And my residual value is how different that prediction is from the actual score. So it is the distance between a person's actual X score and the predicted Y score. Now, this should be randomly distributed. So comparing their predicted scores to their error score should create me a set of dots that is random. So I should just get a bunch of random dots. The other thing we are going to check is multivariate normality using the histogram function and the normal probability plot function. We use the normal probability plot function to check for linearity. So I'm going to go ahead and check on those. And I'm going to hit continue. And then I'm going to hit OK. And by doing that, we get all of our plots for the rest of the assumptions. So, now, univariate normality you can check by looking at each histogram separately. But when you have a lot of variables, that becomes tedious. So for right now, I'm just going to check multivariate normality. So with multivariate normality, you have the histogram where it says random at the top. So where it says random right here, you know that that is multivariate normality. That's your normal. That's your multivariate normality plot. And these are the errors that we want to be distributed multivariate normal. So this plot will show negative and positive numbers because some people's scores are going to be positive and some will be negative. So it should be a normal distribution. When you square everything to create the Mahalanobis distance slash the least squared estimates, that is when everything becomes distributed chi-square and you won't get any negatives. So this plot should look relatively normal. And to look at that, I look at the spread on the x-axis, so on the bottom, so this right here. And the data should fall evenly around 0. However, mine does look positively skewed. It doesn't look evenly spread around 0. I have more over here than I do over here. Now, if multivariate normality plot is skewed, then I would suggest checking your univariate histograms and see which variable is the problem. Now, remember though, if you have at least 30 people, then the central limit theorem kicks in and normality isn't such as big of a deal, and you can kind of bend the rules a smidge. So I'm going to go back to data view. So to look at my univariate charts, I go to Analyze, Descriptive Statistics, and Frequencies. And then I move all my continuous variables over to the variables box. And then I uncheck the display frequency tables. And then I go to Charts. And then I go to Histograms. And I go to Show Normal Curve on Histogram. And then I also go to Statistics. I'm going to go ahead and click on Skewness and Kurtosis. And then I hit Continue. And then I hit OK. So let's look at our first variable, which is anxiety. And I would say that this is not normal. We have some people out by 4 and we have some people out by 8. But then our data looks multimodal, meaning it has multiple humps. So it goes up, down, back up again, then back down, and then back up. So I wouldn't say that this is normal. Now let's look at our stress variable. And I would say that this is normal. We do have a couple out here by 2 and by 7. But for the most part, it looks fairly normal. So I would say it's fine. For memory, I would say this is not normal just because it's bimodal, meaning we have 2 humps. So it goes up, down, and then back down. So by looking at these separate histograms for each of our variables, we might see now why our multivariate histogram is not normal. However, we can also look at the statistics box that we just asked for, which is this box right here. And we can look at skewness and kurtosis. In layman's terms, skewness is how much it leans to the left or to the right, and kurtosis is how skinny or flat the distribution is. Now, this is the same rule as z-scores. So values that are greater than the absolute value of 3 are bad. So if you have any skewness values over absolute value 3, then that is bad. And if you have a kurtosis value over absolute value 3, then that is also bad. And although some of the plots may look bad, the values, if the values are in range that we accept as okay, then the univariate plots are technically skewed, are not technically skewed or kurtotic. So let's look and see if ours are. So for skewness, we don't have any values over 3, over absolute value 3. And then for kurtosis, we don't have any values over absolute value 3. So technically, our univariate plots are not skewed or kurtotic. But I'm still going to say that the multivariate normality plot is still slightly positively skewed. Now the next plot is linearity. And for the linearity assumption, we want the dots to be fairly close to the line, and we don't want a curved shape. And this plot is a PP plot, so it takes a normal distribution and calculates the percentile scores. So the probability at being at each one of these points, and then it calculates the observed people at the point versus the expected number of people, and it creates you a pretty line. So you want the dots to be close to that line. And don't be too picky when looking at this. If you don't have linearity, then you will lose power, and then I would suggest, if you don't meet that assumption, trying a non-parametric test. So for this one, I would say yes, it is linear. We have a couple right here. We have this right here that's, the dots aren't all that close, but for the most part, it's fine. Now the last two assumptions are homogeneity and homoscedasticity. You want this. You don't want heterogeneity or heteroscedasticity. Now this plot is a equal distribution of errors plot. So this is a plot that plots the errors. But the errors should be random, so we compare them to a random distribution. And that is why we use a random variable to compare this against. So we wanted the errors to be random, so we compared them against a random variable. Now, in a real regression, you would just do this against your dependent variable. But with ANOVAs and factor analysis, you use a random variable as your dependent variable, and that is why you make the random variable. So what is homogeneity and homoscedasticity? Well, homogeneity means equal variances. So that means the variance by group is roughly equal. So let's look at the plot where it says scatter plot. So this right here. And you want no raining. So what does that mean? Well, let's get a line across 0 to help us figure that out. So I'm going to double click on the chart, scatter plot. And then I'm going to click where it says add fit line at total. And then I'm going to hit close. And then I'm going to exit it out. And then it automatically gave us a line across 0. So now looking at this line, you want roughly the same amount of dots at the top and at the bottom. So you want the same amount of dots, top and bottom. And you don't want the spread around 0 to be bad. So it goes from 3 to -3, so we're fine. Now, let's say if it went to -3 to 4, you don't just want to look at the numbers. So you don't just, if it did go from -3 to 4, we wouldn't just want to be like, oh, it goes from -3 to 4, it's bad. You want to look at how many dots are at each number. So if you were to draw a line, a horizontal line, at the 4 mark and at the -3 mark, then you would hope, or at the -3 mark and at the 3 mark, you would hope that most of the dots would be between those lines. And even though there is maybe 1 or 2 dots, let's just say if there were 1 or 2 dots out here by the 4, if you drew a line from 3 to -3, that would mean that most of your dots are between -3 and 3, so that would be fine. You also want to look at it the other way, so going up, so drawing a line this way. I haven't figured out how to draw a line going up. I don't even know if there is a way to do that in SPSS, so I kind of have to eyeball it. So looking at your x-axis, the most of the dots are between -2 and 2. It goes from -2 to 4, but like I said earlier, if we were to draw a line, a vertical line now, so 2 and -2, we would see that most of the dots go between -2 and 2. So we were fine there. The other and last assumption you want to check for is homoscedasticity. And it's not that the spread of the dots are equal around 0, but it is that the spread of the dots are consistently spread across 0. Now, homogeneity is that there is roughly an equal amount of people above and below 0, and the spread is roughly the same. But homoscedasticity is that so if you drew a line around the dots, so let me do that. I'm going to copy and paste this into Word so it's easier. And I'm going to go to Insert, and I'm going to go to Shape, and I'm going to click on this right here. So if I were to draw a line around the dots, so if I drew my own squiggle line around the dots, it should be roughly circular or look like a blob. And it doesn't have to be perfect, but as you can see, it does kind of look circular, roughly circular. So I would say that this assumption is met. Now what you don't want, so let me go to my PowerPoints here and kind of show you what you don't want. So now this is obviously the same dots, the same scatter plot that I had before. But you don't want something like a megaphone or a UFO/submarine. So these dots don't make a submarine shape, but I was just drawing you a like what a submarine shape might look like. And that would be where the spread is small on both ends, but large in the middle. So small on both ends, but large in the middle. And this shape would indicate that there are certain areas that you are trying to predict that are better than others, and that is problematic. You want the prediction to be equal all the way down the line. So this was what our shape actually was. It was a blob. And this, it's still the same scatter plot. I just kind of wanted to show you what a submarine would look like, and this would be bad. Now I'm going to go ahead and save this as a new document. Just so I always have this to fall back on if I mess up for my actual analysis. So assumptions. I'm going to hit save. Well, that is it for my assumptions video, which means that is my last video on data screening. And I just want to remind everyone that each individual analysis may have extra pieces that you need to include for data screening, or some pieces that you don't need to include for data screening. So data screening for different analyses may be different, but these 4 separate videos on data screening was just to give you a basic / general idea of how to do the steps in data screening and help you understand what was going on for most analyses, um, but certainly not all of them. I hope each of these videos on data screening has helped you in some way and made learning statistics a little easier for you.